Hello everyone, this is Monica Lupion and I'm gonna solve the example number 2 from the lecture 8, heat exchangers. So please stop the video for a few minutes, read through the problem and make sure that you understand everything that is said. Light lubricating oil with a thermal capacity of 2090 joules per kilograms per Kelvin is cooled using a cross-flow heat exchanger with the shell-side fluid, water, mixed with a heat transfer area of 1.53 square meter. The oil enters the heat exchanger at 375 Kelvin and flows at a rate of 0.5 kilograms per second. Water at 280 Kelvin is available at 1000 kilograms per hour. What will be the exit temperatures of the water and oil for A, counterflow, and B, parallel flow operations? The overall heat transfer coefficient might be taken as 250 watts per square meter per Kelvin. Okay. So first of all, let's draw a diagram. For counterflow operation. So this is our heat exchanger. Oil is flowing inside and water the shell. Water and water. What will be the profile of the temperature? So we only have information about the inlet temperature. In the case of oil is 375 Kelvin. We know that it's been cooled down, but we don't know the temperature of the oil of the outlet. And the water flow is going from 280 Kelvin and it's been heating up. This is oil, this is water. And we don't know the temperature of the outlet in the case of the water. What we know as well is the area is equal to 153 square meter. The flow rate of oil is equal to 0.5 kilograms per second, and the thermal capacity of oil is equal to 2090 joules per kilogram per Kelvin, and in the case of water, flow rate is equal to 1000 kilograms per hour, and the thermal capacity you need to check in your textbook in the appendix, and is 4177 joule kilogram per Kelvin. Okay, so the methodology that we will follow is the NTU, because we know only two temperatures. In the case of the other methodology, the log mean temperature difference, we normally need to know at least 3 temperatures in order to be able to apply the methodology. So this is easier in this case when we only know 2 out of the 4 temperatures of the heat exchanger. So what's the NTU method? First, what we're gonna calculate is the capacity of the system for the hot fluid and for the cold fluid. In the case of the hot fluid is oil. The capacity of the system is the flow rate times the thermal capacity, and this is equal to 0.5 kilograms per second times the thermal capacity, 2090 joule kilogram per Kelvin, and this is equal to 1045 joule Kelvin per second. For the cold system, the cold is water, so the flow rate of water times the thermal capacity of water is equal to 1000 kilograms per hour times 1 hour over 3600 seconds, and times the thermal capacity, which is equal to 4177 joule per kilogram per Kelvin. This is equal to 1160 joule per kilogram per second. So clearly the minimum capacity of the system is related to oil, the hot fluid in this case. Then we apply the definition of the NTU, and this is equal to the overall coefficient U times the area over the minimum capacity, which we have already identified which from oil, and this is the value. The overall coefficient is 250 watts square meter Kelvin. The area is 153 square meter, and the minimum capacity is 1045 joule per Kelvin per second. So the NTU is equal to 0.366. Now we need to calculate the efficiency. And in order to get the value of the efficiency, we're going to use a graph, as I explained in class. This graph is included in your textbook. We can get the value of this efficiency if we know the NTU and also the ratio between the minimum capacity and the maximum capacity. In this case, the minimum capacity is 1045 and the maximum capacity is 1160 joule Kelvin per second. This is equal to 0.9. With these two values, we get into the graph, and the value of the efficiency, it's about 0.29. Why we need to know the value of the efficiency? Because if we know the value of the efficiency at the minimum capacity, we can apply the equation to calculate the heat rate. And the heat rate is equal to the efficiency, minimum capacity, and the delta T of the inlet. So this is the temperature of the oil in the inlet minus the temperature of the water in the inlet. And this is equal to, this is 0.29. This minimum capacity is 1045. The temperature at the inlet of oil is 375. The temperature at the inlet of water is 250 Kelvin. So in total, the heat is equal to 28.8 kilowatts. But the problem is not asking about the heat. The problem is asking about the different temperature. So in order to calculate the temperature at the outlet of the oil and the water flows, we are going to apply the heat rate equation here in the oil flow and here in the water flow. And we know that the heat that we just calculated, 28.8 kilowatts, is the heat that is being transferred from oil to water. So the heat rate that is being releasing from oil is being absorbed by the water flow. So heat, Q, is equal to the flow rate of oil times the thermal capacity of oil times the delta T of oil, and this is equal to 28.8, we just calculated. And this heat is also equal to the flow rate of water times the thermal capacity of water times the delta T of water. From this equation here, we can calculate the temperature of oil at the outlet, and from this equation here, we can calculate the temperature of water at the outlet. So the temperature of the oil at the outlet, heat rate, which is equal to 28.8, it's equal to the flow rate of oil times the thermal capacity of oil, that's the minimum capacity, times the temperature of the oil at the inlet minus temperature of the oil at the outlet. And this value of minimum capacity, this is equal 1045 joule per Kelvin per second. So from here, well, the temperature at the inlet is equal to 375 Kelvin. So from here, you can calculate the temperature at the outlet, and this is equal to 347.7 Kelvin. What about the temperature of the water at the outlet? We apply this second equation here, 28.8 kilowatts, which is the heat rate, is equal to the thermal capacity of water times the flow rate of water, and this is the maximum capacity, times the temperature of the water at the outlet minus temperature of the water at the inlet. Maximum capacity is 1160 joule per Kelvin per second, and the inlet temperature is 280 Kelvin. So you make the calculations, and the temperature of the water at the outlet is equal to 304.8 Kelvin. Okay, in case that we have a parallel flow, the methodology will be exactly the same. We will have to calculate the NTU, calculating first the minimum capacity. Then we need to establish the value of the ratio between the minimum and the maximum capacity in order to estimate the value of the efficiency, and then we can calculate the value of the heat rate, and from there it's relatively easy to calculate the both temperatures at the outlet. So I'm not gonna go through all the resolution again, but I will upload the solution of this section B to eLearners.